Welcome, travelers, to Adventures in Security. In this video, we explore network virtualization and how to secure it. You can download the video script, including the bibliography, from the link in the description. In this video, we're going to demystify virtualized environments and then walk through how to secure them. When I say virtualization, I mean running multiple isolated operating systems, virtual machines, on the same physical hardware using a hypervisor. By the end, you should be able to 1. Name the key elements: hosts, hypervisors, VMs, virtual networking, virtual storage, and the management plane, and 2. Apply a practical security mindset to each layer. I'll use a simple classroom example. Imagine we're consolidating 10 small physical servers into a 2-host virtualization cluster. That saves cost and makes provisioning faster, but it also changes the risk. If an attacker compromises the management plane or the hypervisor, they can affect many workloads at once. So our theme is defense in depth, controls at the host, hypervisor, management, network, storage, and guest levels, plus monitoring and recovery. Let's build the stack from the bottom up. Before we talk security, let's answer: why do we virtualize in the first place? The biggest driver is consolidation. If you have 10 physical servers, each using 10 to 15% CPU, virtualization lets you run those workloads as 10 VMs on 2 or 3 hosts and use the hardware efficiently. The second driver is speed. Instead of racking a server, you deploy from a template in minutes, which is why virtualization is the foundation of most private clouds. Third is resilience. Features like live migration, high availability, and automated restart mean a VM can move away from failing hardware or restart on another host. Now the trade-offs. Virtualization concentrates risk. A compromised hypervisor or management server can impact dozens of VMs. It also adds complexity. Virtual switches, shared storage, and automation tools are powerful, but misconfiguration is common. So think of virtualization as trading hardware problems for platform problems. The good news is we can secure it systematically, layer by layer. In a classroom, I like to draw virtualization as a stack. At the bottom is the physical layer: servers with CPUs, memory, NICs, storage controllers, and firmware like BIOS/UEFI. On top sits the hypervisor, software that creates virtual hardware and schedules real resources. Above that are the workloads. Virtual machines, each with a guest OS and applications. But a real environment also includes the fabric services around VMs. Virtual networking connects vNICs to virtual switches and then out to physical networks. Virtual storage provides shared data stores so VMs can move between hosts. Finally, we have the control plane, tools like vCenter, SCVMM, or Cloud APIs, where admins create VMs, set permissions, and apply policies. When you secure virtualization, you can't only secure the VMs, you also secure the control plane and the fabric, because those are common points of failure. Keep that picture in mind as we drill into each element. Hypervisors come in 2 broad types. Type 1 hypervisors run directly on the hardware. Think VMware ESXi, Microsoft Hyper-V Server/Role, or KVM on a minimal Linux. This is what we typically use in production, because the attack surface can be small and performance is strong. Type 2 hypervisors run on top of a host operating system, like VirtualBox or VMware Workstation. Those are great for labs, but they inherit the security posture of the host OS, so they're usually not your data center foundation. Regardless of type, the hypervisor has 3 jobs: isolate VMs, virtualize devices, and schedule resources. Hardware assist features: Intel VT-X/AMD-V for CPU virtualization, and IOMMU technologies for device isolation make that possible. Here's the security takeaway: the hypervisor is a high-value target. Isolation is generally strong, but it depends on correct configuration and timely patching. So we treat the hypervisor like a critical system, not just the thing that runs VMs. A virtual machine is not a mysterious object. It's basically a set of resources plus a set of files. The resources are things like virtual CPU cores, virtual memory, a virtual network card, and one or more virtual disks. The files hold the VM's configuration and disk data. For example, VHDX files in Hyper-V or VMDK files in VMware. That file-based nature is why virtualization is so flexible. We can create a golden image, an OS that's patched and hardened, turn it into a template, and then clone it repeatedly. But the same flexibility creates security pitfalls. Snapshots, for example, capture VM state for quick rollback, but they also preserve old data and vulnerabilities, and they can grow large and affect performance. One applied best practice is lifecycle discipline. Maintain an inventory, control who can create VMs, and regularly retire old templates and snapshots. If you can't answer what VMs do we have and who owns them, you're already behind from a security standpoint. Networking is where many virtual security surprises happen. Inside a host, VMs connect to a virtual switch, like a software Ethernet switch. We group ports into port groups or virtual networks, often mapped to VLANs or overlay segments. Some platforms use distributed switches, so policies follow the VM as it moves. Now, in a physical network, you might rely on a firewall at the edge, north-south traffic. In virtualization, a lot of traffic is east-west. VM to VM inside the same host or cluster. That traffic may never hit your physical firewall, so if you don't plan for it, you can lose visibility and control. So how do we apply security? We segment. For our example cluster, we might separate a management network, a production network, and a DMZ. Then we add microsegmentation, rules that limit which VMs can talk to which, even within the same VLAN. The goal is simple. If one VM is compromised, the attacker can't easily pivot to everything else. All right, let's zoom in on the invisible network that exists inside a virtualization host. The virtual switch. Conceptually, a virtual switch is a Layer 2 Ethernet switch implemented in software by the hypervisor. Your VMs plug into it using virtual network interface cards or VNICs, the same way a physical server plugs into a physical switch with a NIC and a cable. The switch provides logical ports, and those ports are grouped into port groups or virtual networks, where we attach policies. Things like VLAN tags, teaming behavior, and security settings. Here's the key idea for securing VM to VM traffic on the same hardware. If two VMs are on the same host and the same port group, their traffic can be switched locally and never leave the server. Documentation even notes that if a port group has no physical NIC uplink, VMs in that port group can only communicate with each other, not the external network, because all traffic stays on the host. That's great for performance, but it means a physical firewall or physical span/tap may not see this east-to-west traffic. So, from a security perspective, the virtual switch is not just plumbing. It's a control point where we segment, restrict, and observe traffic close to the workloads. Now, how do we harden a virtual switch? Think of it as doing port security and segmentation, but in software. First, segmentation. Separate management, storage, live migration, and production workloads into different port groups and VLANs. That way, even if a VM is compromised, it can't automatically reach your management interfaces. Second, apply the platform's virtual switch security policies. In vSphere, the built-in security policy focuses on 3 Layer 2 behaviors: promiscuous mode, MAC address changes, and forged transmits. In a typical enterprise baseline, you set these to reject unless you have a specific documented need, like temporarily enabling promiscuous mode for an IDS sensor connected to a monitoring port group. Otherwise, leaving them open can make sniffing and MAC spoofing easier. Third, when you specifically need to prevent same VLAN, same host VMs from talking to each other at layer 2, consider private VLANs, PVLANs. PVLANs let you keep systems in one broader VLAN while still isolating them into private groups, useful for DMZ-style isolation or tenant-style separation. Finally, protect the control plane. Restrict who can change port groups and security settings, and send those changes to centralized logging for audit. Next, let's introduce virtual firewalls, because VLANs alone don't answer. Who can talk to whom, on which port? There are two common patterns. The first is a virtual firewall appliance, a firewall that runs as a VM and routes traffic through itself. That can work, but it often requires hairpinning east-west traffic to a choke point, and that can become a bottleneck as VM to VM traffic scales. The second pattern, and the one that directly solves VM to VM control on the same host, is a distributed firewall. In a distributed model, enforcement happens right at each workload's virtual NIC. For example, NSX Distributed Firewall can enforce firewall functionality directly at a VM's VNIC and supports a microsegmentation model where east-west traffic can be inspected close to line rate. Microsegmentation is just a precise, practical idea. Default deny between workloads, then explicitly allow only required flows. In a 3-tier app, that might mean web to app on 443/8443. App to database on 1433, and everything else denied and logged. Because enforcement is at the VNIC, it still works even when both VMs live on the same host and never touch the physical network. So, how do we actually restrict traffic between VMs on the same hardware platform? I want you to think in layers. Layer 2. Use different port groups and VLANs for different trust zones. If you must keep workloads in the same VLAN but still prevent VM to VM communication, use PVLAN isolated segments so peers can't directly see each other. Layer 3 to 7. Use policy enforcement that can match IPs, protocols, and ports. In NSX-style designs, you build security groups, often based on tags like web, app, and DB. Then write microsegmentation rules and apply them at the VNIC. That's how you restrict lateral movement, even when traffic never leaves the host. If you're in Hyper-V, you can apply firewall-like rules directly to a VM's virtual network adapter using adapter ACLs. A practical classroom exercise is to start with deny any for a VM, then add explicit allow rules for only the subnets and ports it needs. That's least privilege in network form. And don't forget the guest OS firewall. Even if the hypervisor policy is misconfigured, the in-guest firewall still provides a second barrier. The best designs overlap these controls instead of relying on only one. Finally, monitoring. How do we see traffic between VMs on the same host? First, recognize the visibility problem. If two VMs communicate through the virtual switch on the same machine, packets may never hit a physical switch, so a physical span port or perimeter firewall won't help. A classic solution is virtual switch port mirroring, basically span, but inside the hypervisor. On a vSphere distributed switch, you can create a port mirroring session that mirrors traffic from one or more distributed ports to a destination port on the same host, and the documentation is clear that this distributed port mirroring mode doesn't function if the source and destination are on different hosts. In Hyper-V, you can set a monitored VM as a source and a sensor VM's adapter as the destination, so the sensor receives copies of packets from VMs connected to the same virtual switch. Second, use flow telemetry for scale. vSphere distributed switches can export net flow to a collector, giving you who talked to whom, when, and how much, without capturing every packet. Third, use host-level captures when you need deep troubleshooting. ESXi includes Packet Cap-U, which can capture traffic at multiple points in the hypervisor network stack. In practice, we combine packet capture for investigations, flow logs for continuous visibility, and firewall logs to prove enforcement. Virtual storage is the other half of the virtualization magic. VMs usually live on data stores that can be shared across hosts, SAN, NAS, or software-defined storage like VSAN. Shared storage enables mobility features like live migration, because the VM's disk stays accessible when the compute host changes. Security-wise, storage is where the organization's data actually sits, so we protect it like any other critical data store. That means access control to data stores, encryption at rest when possible, and securing the storage network so it's not reachable from regular user segments. Also, distinguish storage snapshots from VM snapshots. Storage snapshots can be a powerful backup building block, while VM snapshots are more of a short-term operational tool. The applied lesson. Design for recovery. Decide how you will back up VMs, where backups are stored, and how quickly you need to restore. Virtualization makes copying data easy. Security makes sure only the right copies exist, and that you can restore cleanly when something goes wrong. Let's talk about the attack surface. In virtualization, the management plane is often the keys to the kingdom. If an attacker gains admin access to the management server, they can power off VMs, change networks, mount disks, or clone sensitive systems. Hypervisor vulnerabilities and VM escape attacks are less common, but they are high impact because they break isolation. More common in the real world are misconfigurations, exposed management interfaces, shared admin accounts, weak segmentation, or unpatched components. Another risk is data leakage through templates, snapshots, and copied virtual disks, because a VM disk is essentially a portable hard drive. A current example, CISA and partners have warned about Brickstorm malware being used by PRC state-sponsored actors to target VMware vSphere environments, including vCenter and ESXi, to maintain long-term access. The lesson isn't be afraid of VMware. It's protect the control plane. When attackers go after virtualization, they often aim above the guest OS because the payoff is bigger. Now we move into controls. First layer, the host and hypervisor. Start with attack surface reduction. Use dedicated virtualization hosts. Don't browse the web or run extra roles on them. Follow the principle Microsoft emphasizes for Hyper-V. Minimize the host OS installation. Keep firmware/drivers updated and manage hosts remotely whenever possible. Next is patching. You patch three things: firmware, the hypervisor, and the management tools. Build a maintenance cadence and use live migration or clustering features to patch without major downtime. Then secure boot and trust. Enable UEFI, secure boot, where supported. Use TPM-backed features, and prefer signed modules and verified boot chains. On many platforms, you can also enable lockdown or restrict direct shell access, reducing the chance an attacker can log into the host and hide. Finally, baseline configuration. Use vendor hardening guides and community benchmarks, like the CIS benchmarks for VMware, to standardize settings such as disabling unused services, enforcing strong authentication, and centralizing logs. Second layer, the management plane. Treat vCenter, SCVMM, or your cloud control portal as a Tier 0 asset. similar to a domain controller. Start with network isolation. Put management interfaces on a separate VLAN or physical network, and only allow admin access from a hardened jump box or privileged access workstation. Then implement strong identity controls. Use MFA for all privileged accounts, and use role-based access control so admins only get the permissions they need. For example, a help desk role might power cycle VMs, but should not modify networks or attach disks. Also separate accounts, one for daily work, one for privileged tasks, plus a monitored break glass account for emergencies. Don't forget API security. Many attacks use automation interfaces. Restrict API endpoints, use certificates properly, rotate keys, and log administrative actions. Centralize logs from the management plane into your SIM and alert on high-risk events, like new admin creation, mass snapshotting, or changes to security policies. If you protect the control plane, you prevent the one compromise, many VMs scenario. Third layer. The guests and the data. A common misconception is that the hypervisor handles security. It doesn't. Each VM still needs the same basics as a physical server. Secure configuration, patching, least privilege accounts, firewall rules, and endpoint detection where appropriate. But virtualization adds extra opportunities. Use hardened golden images and keep them under change control. Patch them, scan them, and reissue templates regularly. Consider enabling security features like secure boot, virtual TPM, and VM encryption where your platform supports it. These help protect VM integrity and secrets even if someone gets access to the VM files. Also manage the data artifacts of virtualization. Snapshots and cloned disks can contain credentials, tokens, and sensitive files. Limit who can create them, encrypt backup repositories, and set retention rules so snapshots don't live forever. In practical terms, treat a VM disk file like a laptop hard drive. If someone copies it, they can often read everything on it. Security isn't complete until you can detect and recover. Monitoring in virtualization means collecting logs from multiple layers: the hypervisor, the management server, and the guest OS. Forward them to a central log system, time synchronize everything, and build alerts that understand virtualization behavior. For example, unusual logins to the management plane or a spike in VM exports. For east-west traffic, consider virtual network telemetry, distributed firewall logs, flow logs, and internal IDS sensors. Remember, attacks often spread laterally between VMs. Now recovery. Keep backups that attackers can't easily destroy. That usually means immutable backups, offline copies, or separate credentials. Test restores regularly, not just the backup job succeeded, but we restored and the app works. Also write an incident response playbook for virtualization. What do you do if a host is suspected compromised? Typically, you isolate it, capture evidence, rotate credentials, validate management integrity, and rebuild from trusted media. Virtualization makes rebuilding faster if your backups are clean. Let's wrap up with a checklist you can actually use. Step 1. Design. Separate management from production networks and segment workloads so the blast radius is limited. Step 2. Build. Harden hosts and the management plane using trusted baselines and create golden images for VMs. Step 3. Run. Patch on a schedule, monitor continuously, and practice recovery. Here's a quick 10-step summary. 1. Dedicate and harden hosts. 2. Patch firmware, hypervisor, and management tools. 3. Isolate management networks. 4. Require MFA for admins. 5. Enforce or block in separate admin roles. 6. Secure virtual networking with segmentation and microsegmentation. 7. Encrypt sensitive data and backups. 8. Control templates, snapshots, and VM exports. 9. Centralize logs and alert on admin actions. And 10. Keep immutable backups and test restores. If you take nothing else from today, remember? In virtualization, the control plane is powerful. Secure it like your environment depends on it, because it does. That's it for this video. If you learned anything, please remember to give us a thumbs up and subscribe. And until next time, be careful what you click.